Today, we're going to talk about resistor and capacitor combinations. Capacitors in parallel and resistors in series simply add together. You add together each individual component to get the equivalent component. For example, if you have three capacitors in parallel, you add them together to get one equivalent capacitor. When capacitors are in series and resistors are in parallel, though, you must use a slightly different equation, where you sum the reciprocal of each of the capacitors or resistors, and then take the reciprocal of that. When solving this type of equation, the most important thing to remember is not to forget flipping the fraction at the end of the problem. In our first example, we have a network of resistors. We would like to find the equivalent resistance of the circuit and the current supplied by a 12-volt battery. We'll begin by noticing that two 4-ohm resistors can be combined because they are in series. Resistors in series add, so we add them to get one 8-ohm resistor. Our second combination is two 8-ohm resistors that are in parallel, so we plug our values into the equation for parallel resistors. 1 over 8 ohms plus 1 over 8 ohms gives 2 over 8 ohms, which can be simplified to 1 over 4 ohms. 1 over 4 ohms is not the answer. We still need to take the reciprocal of both sides of the equation in order to get equivalent resistance equaling 4 ohms. Updating our drawing, we now notice that we have three resistors in series that we can simply add together to get our final equivalent resistance of 16 ohms. To solve for current, using Ohm's law, we recognize that current is voltage divided by resistance, which is 12 volts divided by 16 ohms. The current is 0.75 amps. In our second example, we have a network of capacitors connected to a battery. We would like to find the equivalent capacitance of the circuit. The first capacitors that we notice that can be combined are the two capacitors on the right, which are in parallel. Parallel capacitors add, so we add 5 microfarads to 4 microfarads to get 9 microfarads. Now, the next two capacitors that we combine are in series, so we use the series capacitor combination equation. Here, we multiply each of the fractions to get a common denominator, and then we can add them to get 11 over 18 microfarads. This is again not the answer. We still need to take the reciprocal of both sides in order to get our equivalent capacitance of 18 over 11 microfarads, which is roughly 1.64 microfarads. So, our final drawing of the circuit with one equivalent capacitor looks like this.